Okay, here we are again. Now we're going to do an amplifier, loop amplifier. Here is the circuit we're going to do. Some of you will recognize it over here. This was taken from the web, so hopefully there are no issues. Just using this as an example of building an amplifier and simulating it. Okay, so I'm going to move this onto another screen, and you can see it build up as we draw the schematic in Spice. Okay, so let's start Spice. Start a new schematic. And let's start by building up the transformer, input transformer. I'm going to zoom out here a little bit. Flip this over. Oops. And then see, they have a bunch of windings on the front. Let's put one up here. Now for the middle winding, they have a center tap. So we can either just put two like this and wire the centers together, or we can actually lay the centers on top of each other. When I click this, those will connect like that, and we can hook wires to that point later and then put the lower wire down here, lower winding down here. Now let's move this more to the center. Okay. Oops, the input winding is also double, so let's put it here, or center tap, I mean, like that. Grab another inductor and stick it here. Okay. Now we have the transformer set up. While we're at it, we may as well define the coupling coefficient, K1, and we have 6 inductors here, L1 through L6, it looks like. L1, L2, L3, L4, L5, L6, and we'll do the obligatory 9975 for the coupling coefficient, and put this down here somewhere. Okay, I'm going to zoom out a little bit. Okay, what are we going to do next? Let's grab a couple of transistors. Now, we go to the components. We grab an NPN transistor. And the way this schematic is drawn, we need to rotate bottom one like this. And it looks like maybe in here somewhere. And then top one like that, roughly. Yeah. Okay. And then just to help me avoid confusion, I'm going to go ahead and wire those up. I don't quite have that centered, but that's okay. All right, and then the bases look like they are connected to this. I did that right. Yeah, they have some ferrite beads in there, but ferrite beads aren't going to really make much difference in the Spice model. We have everything's perfect here. We could put them in, but I'm going to leave them out. for the time being. Okay, then we need some resistors in the middle here for the biasing. They have a 100 ohm pot. I'm going to just set it to with two 50 ohm resistors tapped in the center, because Spice does not really have a good pot, believe it or not. You can fake one up. I've done it, but it's usually not worth the trouble. We need a capacitor across that, and a couple more capacitors up here. And that's about right. And we wire this stuff together. Click, lots of clicking here. Okay, looks like we need a ground over here. And may as well fill in these component values. Right click. This is 2.2 microfarads. Okay, remove that. And right click on this one, it's 50 ohms. Ohms. And these caps are 100 nanofarads each. I believe you can put N instead of NF, and it works. I put NF. And then I need to hook those up to these feedback windings. That was the line right up. Okay, coincidence. All right. Let's stick a ground over here on the center tap, the input. That. And we need to bring this guy. Let's see, maybe. I just need to get it up somewhere, so let's put it up here somewhere. And leave that dangle for now. Okay. Now it looks like I need an output transformer, so we've got to build that up over here. And that's center tapped to center somewhere around there. And the secondary winding is not center tapped, so we put it there. And let's see, I may as well create a coupling coefficient for that, K2. And it's for L789, L7, L8, L9, 0.9975. Stick that down here somewhere. Okay. And we hook the collectors of these transistors to the output. And we're not going to wire the secondary to the AC ground on the power bus. I mean, we could, I guess, but it really doesn't make a whole lot of sense for this case. I think the only reason he did that was to put 0 volts DC across the output coupling cap, but um, functionally it's not going to make any difference. So let's build up the power circuit up here. He has an inductor located somewhere around here, and it is a 1.5 millihenry. We're going to need a power supply, so let's go into the components and get a voltage. Put it over here, right click on it and just set it to DC 12, 12 volts for now. Okay, give it a ground. And then we need, looks like a 2K resistor. Turn that sideways. Put it about here. And then over on the left, looks like we need a resistor here somewhere. Then we need a bunch of capacitors. Then we need some grounds. Just sort of drawing it as close as I can to the way the other circuit was drawn, the original circuit. Now let's hook up the power bus. Oops, messed that up. A little shaky. Okay. Click. Come over here. Okay, getting close. Oops, forget the ground on the 12 volt supply. Okay, now we need these. These caps are 330 nanofarads. Right click, 330 NF. This resistor is 2K. This resistor is 1.2K. And let's move that a little bit neater here. And then these caps are 100 nanofarads each. Okay. Okay, now we need an input voltage source to drive this thing. Stick it over here. It's for fun. Pick an AC source. Maybe a 1 millivolt. Why not? Doesn't matter. And give it a source impedance of, say, 5 ohms or something. and look it up. And I'm going to change the name of this to BI. And then we need a load, the output over here. And to make Spice happy, we need to ground that floating loop there. Okay, and then looks like I forgot to hook the power up. That goes to the power bus. Okay, and then I need to get this to the bias supply. And there's a 10 puff cap I see sitting across this winding. So okay, so the basic amplifier is done. Oh, we haven't picked the transistors. Now, right click on here, pick new transistor, sort by part number, and then go down to the bottom, and lo and behold, the ZTX transistors here. Now, if you just download and install LTSpice from the website, that won't be there. I had to add this myself. You could use a 2N4401, or I believe that might be in the library. I can show you how to add stuff, and maybe in another video, or maybe at the end of this one, I don't know. Right now, we'll just grab it out of here and set that to the transistor. And same here. Right. If you don't like the text like that, I think we can rotate it. Justification. We don't want vertical text. And we may as well do that here too. Okay, there we go. Now we're going to go over to the file menu, and we're going to do a save as, and we're going to call it Wellgood1. Okay, and that'll become an ASC file, which is a schematic file for LTSpice. Okay, now there's still some issues here. We need the inductances for these windings. We can either calculate them or we can parameterize, as I showed you in the video number 3. I think I will just stick some inductance. Actually, what I should do is parameterize, so I guess I'll do that now. So let's stick the parameters over here somewhere. Okay, well, I guess they're going over here, given the way I zoomed. And start with input NI, input transformer, primary, yeah, that's good. Need a dot param. Dot param. Hardest part is figuring out the reasonable names for these things. Number of turns on the input transformer primary. And let's see, according to this will be a half, so it'll be 7 turns. And I'm not going to put comments. Stick this over here. I'm going to have a bunch of them. param NIS secondary is also going to be 7 turns. It's actually half again. And we need the feedback winding. Param NIF, and that's 1 turn. And then we're going to need the things for the output transformer. And OP, and that is 8. Oops, not param. NOS, output secondary, and that is 6. And then we need the AL of the cores. Oop, dot param L. Close enough. And then we need to calculate all of these inductances. Dot param LIP, input primary inductance, equals AL times, what's it called, NIP, P squared, star star, 2 times 1E minus 9, as I described in the previous video. Dot param LIS equals AL times NIS squared times 1E minus 9. Dot param LOP equals L times NOP squared when E minus 9. Probably should have paused the video to do all these, but I'm an amateur at making these, so I'm allowed. And it won't be that much longer. LOS equals AL times LS. And there we are. I think we have everything calculated. Now we just have to go assign them. Brace, LIP. I'm not going to bother moving everything here because it takes too long. Brace, LIP. Brace, LIF, the feedback inductance. Brace, LIS, secondary inductance. Brace, LIS. Trace F feedback. Trace LOP primary. Trace LOP another primary. And last but not least, trace LOP, S secondary. And forgot to give a load resistance here, 50. I did leave out that 2.2 microfarad coupling cap out here. I guess I could add that. It's really not going to make much difference in terms of what happens with the amplifier. So in the interest of saving time, I'll skip that. Okay, there it is. Should be complete. Now we go back over to File and click Save this time since we already named it. And we should be ready to run a sim on this. I guess we'll find out if there's any problems when we try to do that. So now in this case, we want to run an AC analysis, which is a frequency sweep. That's usually what you're interested in. With these, you could run a transient also just to see signals going through it, but here we're just going to do an octave sweep, 100 points per decade, start at 10 kilohertz and end at 30 megahertz. I always forget I think if I put lowercase m, it tries to do millihertz or something. And I always forget for sure what to put for megahertz, so I just put E6. It's the inductance for L5, so I missed an inductor somewhere. Okay, that's fine. So I did something wrong here. Yeah, I never calculated it. I forgot to calculate LIF. So I need a dot param LIF equals AL times NIF squared times 1 minus 9. Okay, now let's see what happens. And it ran. Okay, now I'm going to do the simple thing here to start with and just look at the output voltage. Now I'm looking at here is voltage. So we can see the response, but it's not a gain, it's just an output voltage. Okay, and it's plotting the phase for me, which I'm going to right click on that axis and say don't plot phase. So that's what our frequency response looks like. Right or wrong, not too hot. Okay, I don't know if we've done something wrong or if that's really what the amplifier does. Pause this. Oh well. I would I made a mistake. Well, maybe one of these input things is not hooked up. Let me zoom this. Maybe I did a bad job connecting. No, looks like they're hooked up. Oh, this is. Oh, I used V1, not VI, and so I grabbed the wrong source. I bet V1 is the DC power supply. So I got to go back and edit that. Let's shrink this back down, edit it. Yeah, I have V1 there, not VI. So we change this. To VI. There we go. That's the amplifier gain. Not the output voltage, but the amplifier gain. Now notice again, because we didn't put a square root on it, this is actually double what the real gain is. We can fix that by editing this, sticking sqrt inside of set of parentheses here. Okay, now this scale should be correct, and says the gain is sitting at around 32 dB. Okay. Now, one thing to tell you is that when you select the schematic and save it, it doesn't save your plot. To save the plot, also, you have to select the plot and do save plot settings. You can also save plot settings as and leave the plot setting, give it a name. So I believe it'll use the name that's related to the name of this by default. Okay. So that's it. We did it. The end.